So let's get started. I do notice that this is midterm weeks, so we're having a lot of people are very tired, including me. I mean, although we don't have midterm, but we are pretty exhausted at the middle of the semester. Hopefully, we will soon recover because as the uh, autumn kicks in, the weather getting cooler. So hopefully, we're getting more awake. Just a very quick review of what we have said last time, which is talking about the random variable, because today we will get into the business of sampling distribution. So just to remind you that there's some Excel thing we have covered last time is do the norm.dist, norm.dist and Poisson.dist, and hypergeodist and exponential dist and normal dist. And this is are the way that you would be do the calculation much faster than the standard formula. And we do ask you to work on it for your assignment. Just to remind you that assignment will be due, I think, 10 days after. It's been there for quite a while, so you still have I think the due date is next Thursday. So, but we only have 7 questions, so you still have more than 10 days. So each day you do 1 question is already sufficient to do it. And it's not something too difficult. As long as you understand the green example working, you should be able to do it without too much difficulties. And I think we will soon have an optional tutorial where the tutor will go over the assignments and review what we have been doing. So it's optional. So I think he will also record the class and then you can take it if you have time. If you know already what's going on, then you don't have to worry. It's just optional in case you really want to have a review. So before we start, is there any question so that I can answer quickly without okay, so we're done with the first part so of the course, so I guess it's good to start immediately on the second part. So sampling distribution, as you can see, that is also a distribution, probability distribution, and we talk about looking at data, okay? And data, as you understand, is not known before you collect data, and it depends on which observation you collect or which individual you talk to, and then that will determine your data. Okay, so that's why we need to study probability, is because of this idea. Okay, so a quick terminology discussion. First is the population, which it's saying what we would like to study, we would like to draw a conclusion on, and in general, this is the thing that you're interested in, right? Suppose you are a business owner, you want to know how much people will spend on your new product, right? And then you're interested in whole Hong Kong market, or the whole market, or maybe even Greater China or Greater Bay Area. And unless you are able to talk to everyone in the market, you don't know how much to pay, right? Or you are able to talk to everyone in China, right? Probably it's not possible, right? And even if you have data, right? Say you can able to ask everyone in China, the data size will be too huge to do analysis, right? You have 1.3 billion people, right? How can you have access to that data? To analyze that data will take a lot of time. And even like you work for government, you have to get that kind of data. Usually government don't allow you to access the full set of data, even your government employee, because of due to the safety and security and privacy reason, you only allowed to get some part of that. right? So even if you are government or a company, so suppose you are Meituan, right? You are DD, you have the also almost monopoly of the market, but you don't allow it to have the access to whole company data. But also uh, you only have data in the past, you don't have data in the future, right? Unless you have access to a crystal ball, know the future, you don't have know everything you want to know. So you still have to, based on what you have, to guess what's going on in the thing not study, right? Data is the thing in the past, so you don't really know the things about future. So we are going to do is go a sample, right? If you want to predict the future, use the past data, right? The stock price, right? Use the historical stock price to predict what's the future stock price, right? Or you want to know a geographical idea, you may know how much people want to pay, right? Based on some survey of some selected group of people, and then to guess what's going on for the general, right? Or you want to use the Hong Kong market idea to guess when you want to branch out to Shenzhen, then that's how you want to expand your business based on what your existing knowledge. So that's called sampling. Okay, so that is the idea, right? So whenever we do business decision, it's always related to uncertainty, right? Because you don't know everything well, so you have to use your domain knowledge, your data to do educated guess, right? Otherwise, how can you are able to do it, right? Suppose that these days a very famous thing is what we call low altitude economy, right? Looking about the drones, looking about uh, unmanned vehicles or uh, low altitude taxi, right? In that case, I mean, it's very difficult to know what's going on because we don't know the market size, right? And we have to rely on some survey idea, right? And how things operate in other related business to make idea what's going on there, right? So we have to make some guess, right? And this is always have to do in business, okay? So I hope I convince you that most of the time you don't have population, okay? You only have sample, okay? And even your data you are not allowed to access. So uh, in most cases, this is what we have. The sample is what we have. And in terms of terminology, have to be a little bit more careful. The population, say, suppose you care about how much they want to pay for a product, right? And suppose if you know everyone, you can draw a histogram, right? You can draw the relative frequency, right? What proportion of people like to pay this much, right? Then you will have a F, the relative frequency table, right? Or actually same as the P, right? And you can have mean and variance. And this mu and sigma square are numbers, right? Are numbers. If you know the population, you know them, right? And they are not probabilistic. There's not random variable. You just don't know it. There's number there, but you don't know it. Okay. So there's no probability related to mu and sigma square. They are fixed number, but you just don't know them. Okay. And what is random is the way you collect the data, right? You don't know before you collect data who you would be able to talk to, right? You may be randomly pick up people, right? Talk to, say, in the subway station, or you go to library and ask people, or you go to the on the street, or you random call, right? Or online survey, you don't know in advance who you talk to, right? You don't say you talk to this particular guy and this particular guy would like to talk to you, right? Because people randomly reject your call, right? So you don't have observation to those, okay? And that means that you would be usually doing a random sample, right? Which you would randomly pick up some people, and who you actually pick up is follow some uh, random variable, right? Supposed to collect how much they want to pay, right? If you collect just talk to randomly pick up one guy, the likelihood you pick up that guy is random, and that means that the distribution of that number you're going to record will follow the same f as the f above. Okay, so the relative frequency, okay, indeed become the probability function or polymass function or CDF, the big P and big F, actually will tell us what's going on in the F, right? You can imagine if you collect a lot of data, right, the distribution of the data should closely align with the population one, right? Suppose you talk to everyone, right? Suppose say, then the data you get, right, will be exactly the same the population, right? And if you talk to almost everyone, then the distribution what you get should be similar to the F, right? And of course, you don't talk to everyone, so we are not going to able to guess what the F is. And in general, what I'm interested is to go looking at the mean and variance. That is something we can estimate pretty well. I mean, you want to do other things will be very difficult, but in general, in this class, we mainly focus on the mean. Of course, sometimes variance. As we said, variance is about measuring the risk, right? In finance application, that will be something you do in finance a lot, right? And the mean is also very interesting because when you do investment, right, you care about the average return. So that would be something we care about. Of course, these days we want to care about kurtosis and skewness as well. But these two are the main thing we are looking at, and you want to do skewness kurtosis will be other classes. You can also do that in similar what we have been doing, but we're not focusing on them. So because everyone you talk to, suppose you talk to N person, everyone you talk to is a random variable because you don't know who you talk to, right? If everyone is a random draw, and you denote this a capital letter X as the standard notation. Capital letter refer to random variable. Okay, small letters refer to the numbers. Okay, capital letter is something that we don't know the value yet. So we have been using this idea a lot already. Okay, so we focus on what we call for our math derivation, we focus on simple random sample. Although the name call is simple, actually it's very hard to achieve due to a lot of constraint in the world. But let me tell you what it is. The simple random sample is the most basic way, which means that you have every individual that in the population have equal likely to be selected, and each element is going to select independently. So let me give you an idea what is behind, right? Imagine you're focusing on things in Hong Kong, right? So you want to know how much they want to pay for a product, right? And maybe that's Mr. One, right? He's is not very rich, right? So he's only willing to pay for $1 for the product, right? And maybe a woman number two, she has more money, right? She has willing to spend $2 for that, right? And there's another elderly number three, right? He he really like the new product. He want to try it out, and he want to spend $3 on the product, right? And consider there's another guy, little baby, right? Little baby, okay. Baby number four, right? He's only willing to spend $4 on the product, okay. So simple random sample means that if you pick how to pick, okay, everyone likely pick up. So if I basically I would have to talk to say toss a coin and roll a die, okay, maybe end up with Mr. Number One. Okay, that's my first observation. And my second observation, I toss a coin or roll a die or whatever random mechanism, I may pick up the number one again, Mr. One again. So this is allowing simple. I may able to talk to the same guy again. I can be number one again. That's possible. Okay, and and picking number one can be do it again, and also I can pick number one, number two, number one, number two, number two, number one, right? And then they may be couples. May possible if you ever talk to the man that often, the woman will be angry because you ignore her or some whatever reason, right? Maybe the same family you don't want to with the same family again, right? And in that case, in this example, also a problem of maybe the baby can't talk, right? So how can you pick the baby, right? The baby don't have the consent or don't have the intelligence to talk to you, even though he really like the product, right? Or the old man, maybe actually the old man in the actually in the seniority house, which you can't really talk to him, or you're doing a survey using the internet, right? He or she may not be able to handle the complicated survey, right? So that means that simple random sample is not so simple to implement, because everyone have to be picked equally likely, and choosing one of them, right, can in the past doesn't happen affect the future, right? You can able to pick the same guy again, 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 again. So that is not something easy to implement, right? But nevertheless, we have that because it will simplify our math calculation. If choosing one guy can affect the woman, right? Suppose they're a couple, right? You probably want to talk to one of them uh, because maybe they have a family budget, right? They have the whole budget controlled by the woman or the man, or at the joint account. So if the man buys the product and the woman don't want to buy it, right? Because there's no point, right? Because they would be buying only one unit, say, suppose, right? Maybe you're talking about, say, TV, a new TV, 8K TV at home, then probably the man buy it, the woman, well, we don't buy it, or right, because they don't need two TV at home, right? For example, right? So that is the idea behind. So that is not something easy to implement. But in our class, we just assume that's possible to do it, and there are many ways to make it possible. And as I said in the uh, uh, later, we see the next slide how to implement those. But a simple random sample, what it buys us, okay, although it's not really realistic, that buys us a lot of things. The first thing is every random variable means as observation is independent. Okay, and later you see the independence helps a lot, because you remember from the last class we say uh, variance or sum of the variance, right? If they're independent, and this is the key that we rely on that. Okay, and also because of independent means that each observation will follow the same big P and big F or small f, right? So that means that our calculation will be very easy, right? And that is somewhat idea behind our binomial, right? Binomial is each trial, which when you open each box is going to be independent. So that is the main thing that you will see is behind. So we are not looking at hypergeometric idea, but it's rather we're looking at binomial. Okay, so it's each observation, is the yes and no is going to be the same. Okay. So as we said, they have the same big P and same big F. You will imply the following idea, right? They have the same, each observation would have the same mean, okay? And same variance and zero covariance, okay? We have said already. Means each observation is independent. And of course, you imply the same kurtosis, skewness, IQR, range, mode, median. Each one will be the same, okay? But that would be something uh, important. As I said, that would be not easy to implement in practice. The main idea is because of the real world is not independent, right? People with the same background likely to live with each other, right? Even I look at this room, the one who sit next to you will likely to be very similar to you. Maybe you're coming from the same program, you know them, right? At least you don't hate their smell, right? Otherwise, this is so hot now. I mean, these days, right? And then at least it's not, you don't hate his face, right? Or right, whatever reason you sitting next to each other, right? So then if I collect data from you and the one sit next to you, likely you're correlated, right? There's no, it's not zero correlation, right? Or if I go to collect data in the library, which often we do in the student survey, there's a problem, right? Because if you want to use that data from the library to extend this knowledge to everyone in CHK would be wrong, because people to the library probably is different from the people who don't go to the library, right? So if you only want to, your population is care about who people go to the library, that's fine. But if your population is going to infer, it's going to say the whole CHK student body, then it's an issue, okay? So that has some way to do it. You have to what we call, something is called certified sampling, right? So you have to make sure that not all your data come from library, right? Some data come from the people with the library, some sample coming from people who study in the coffee shop, some people who study in the I don't know, in your hall, or some people would like to go to Starbucks or elsewhere, right? So then you have to able to figure out some way to do it, right? Suppose you want to do online sample, then probably you also have to do some offline as well, right? If you do it in, say, CHK, then also you want to do it in Hong Kong U, CTU, or at other school in Hong Kong if you care about the higher education, right? So that is something that have to keep in your mind. I mean, of course, not too important in your class, but if you really want to take into practice, doing the business or in other cases, this is something you have to keep in your mind because, again, garbage in, garbage out, right? Statistics technique doesn't turn rubbish to gold, right? So you have to have some gold within your raw material. We can distill the gold from it, right? There's no magic there, right? Statistics just abstracting, distilling the information from the data, right? So if data is rubbish, then you can turn rubbish into something good, right? So have to be very careful here. There are a lot of cases they think that they have advanced technique and going to help, but it's not, right? Even though look at the AI or large language model these days, right? They rely on very good raw data. If they don't have the raw data, then no matter you spend billions of dollars training your model, it's not going to work, right? And you do notice that probably 10 years ago, well, no, 8 years ago, right? Probably, I think you guys are still in the high school. No, maybe primary school. Probably primary school, right? One thing is very famous called AlphaGo, which is by the deep mind by Google. It is time where human is being defeated by the most smart people is being defeated by computer, which believe it's impossible for computer to win the Go, right? The game that is a black and white uh, pieces, right? And you don't notice that. I mean, how the AlphaGo is being trained is based on the human textbook on the Go, right? Then they learn from that. I mean, even that they already beat the best guy, best human. But since then, they have the AlphaGo Zero, which start from scratch, right? And then they use AI to they use one AI versus the other AI, and that's how they learn. And that AI is so much stronger than the one trained by human. Why? Because they don't have the crappy data, right? Human have some way that isn't smart enough, right? That we can't exhaust everything. But if the computer can so fast, right, and then they're able to generate new data, they're able to learn much faster. So and that's why these days you can see Elon Musk or other AI is doing is trying to create fake data to train AI. Okay, I don't know how good it is, but maybe there's something behind there as well. But now we want to talk about one thing in the class. I mean, you will be wonder why we talk about this in the middle of semester, right? Everyone remember what's the name of our course? I know you know our course code is 2011, but what's the name of our class? Do you know anyone? Anyone remember the name of our class? Name of a course. What's the name of a course?
Statistical analysis statistics.
Right. So what is the first word?
Statistical.
Yeah, statistical, right? So far we didn't talk about statistics. I don't know whether we're surprised by that, but let's define what is statistics, right? But so far we didn't define anything about statistics, right? And then we only be able to define the midway because statistics is not well defined until we talk about random variable. So what is statistic? Statistic is a function of sample. What do you mean by that? It's a rule that you give me the data, okay? I give you a number, okay? Do remember the data is a random variable, okay? So statistics is a random variable, or formally it's a function of random variable, and that means that it's a variable, random variable, right? Because function is you give me something, I output something. If your input is a random, of course your outputs are random, right? So remind you again, statistic is a random variable, okay? It's a function from samples, okay? So statistic is not a number, okay? It's not a number, it's not a fixed number. It's a rule that you give me a You give me a sample, I will give you a number. But before you give me a sample, you could collect the data. It's a rule how you convert the data. Okay, and basically is what we call data summary or data reduction, right? Because you give me a very big data set, okay, and this will tell you a number, right? For example, is sample mean and population and sample variance. What does it mean, right? It's like if before you collect data, I tell you that if you collect data, how you get one thing, right? So that is different from what we learned, the population mean and population variance, right? Population mean and variance is like the data is there, you try to summarize it, right? So say, remember the question, you say, okay, your boss gives you data, right? So a lot of data, then you try to simplify it, right? So it's given data, you simplify. But now this is a random variable. It's before you collect. I tell you that once you collect it, how can you simplify it, right? But before you collect, you don't know what it is. So that's why I can't tell you what it is. It's a rule to simplify your data result. Okay, it's a rule. Okay, it's not a number by itself. It's a rule that you simplify your data, and your data is not determined yet, right? Before you collect, right? So it's a very important concept that is different from what we learned. So that's why we have to wait until today to talk about this. Although our class got statistics, right? We only do it now because data is a random thing. It's not something that is there, right? Or because someone collect for you, it's there, but doesn't mean that before you collect it is deterministic, right? It's a random thing. Okay. I think that's very important to aware that you only observe one universe, right? Potentially there are many universes that's possible you might observe, or you can imagine the future is not determined yet, right? Of course, that runs to the philosophical question whether there's a future in the past, but I don't want to get into the idea that the future is determined, right? But just saying that the future is undetermined, right? This better, right? Otherwise, what we're doing here, right? So here, let me review what we have here, the sample mean. That is different from the mean in the old days. The mean in the old days is just adding all the data, observation divided by n, okay? Observation and numbers, right? But now it's different. We're adding random variables. The big X are all random variable. Remember, look at the chapter 1. Our all notation there will be small letter. Now everything is capital letter to let you know that each capital X are random variable. We did not know them, but once we met one guy, we know the X. We know the other guy, we have X too, right? We have all N guy we met, then we will have the number. But we haven't met them. But I tell you that how you do it before you do it. Okay? Do you understand the difference? This is called the sample. Okay? And remember, it depends on the sample you get. So this is a random variable. Okay, so have to be very careful about this point. So we will tell you that how this sample mean looks like because this is a random variable, right? You have a you can use if it's discrete, you would be a have you can describe by big P, right? Or big F, right? If continuous, you can also use the big F or small f. Okay, and turn out will be easier to focus on its mean and variance first, okay? And we will talk about what's the big P and the big F, okay? Later, okay? Today, okay? And it turns out, as I hint in the last class, the big P, the shape of this sample mean will be when the sample size is the bell curve, okay? We'll talk about this very soon, okay? This is non-trivial. The result is known as central limit theorem. So it's why it's non-trivial because I didn't say anything about the underlying population. Okay, the underlying population can be very crazy shape. Okay, and the sample mean will be a bell curve. So let me illustrate this idea here. Okay, So the underlying population, right? Say suppose how much people want to spend on your product, right? Can be anything you like. Okay. Okay. Can be any shape you like. The distribution can be, right? It's big F here, right? Or you like it's a P here, it's fine, right? It's like depend on you like this big P or small f, right? That's up to you, right? If big P, then will be bunch of bar chart. Okay, small f will be like this, right? Make it continuous, easier to say. And we do know that what's going on is the sample mean. Okay, sample mean we look like this, right? Suppose we do simple random sample, which means that we're going to draw something from the orange, right? Randomly pick one guy, right? Then we will meet one of them. Can be something comes out, right? We don't know which one we meet, but something like come out this guy, maybe come out this guy, come out this guy, right? Depends on who we meet, right? If you meet 3 person, maybe end up with this 3 guy over there, right? And the average will be just average 3 number of those, right? And then depend on this sample, then the mean maybe end up here, right? And you draw the other 3 guy, the mean average will be maybe somewhere here, maybe somewhere there, right? The mean just like this. Remember how to calculate mean? Mean is like somewhere here, go to left and go to right, the same distance, right? That's the mean, right? And the sample mean can be depends on where they are, okay? And turn out, it's very important, is if you do a last sample, at the end, it is always a bell curve, regardless of initially what you're doing, okay? I don't have to know what is going on in the population. It turns out the sample mean, when the sample size large, is always a bell curve. Located, this whole distribution have an overall mean of, this may not be here, right? The overall mean of this can be somewhat like mu is here, variance sigma square, okay? This sample mean will also have center at the mu. Variance will be sigma square over n. N is the sample size you're doing. Okay, this is the most important, I would say, theorem in statistics. It's called central limit theorem, which essentially sample mean will be a bell curve when the sample size large, regardless of what the underlying population looks like. The population can be binomial, can be Poisson, can be uniform, can be hypergeometric, can be anything in your head, can be just random mountain like this, or can be U shape, can be V shape, can be W shape, right? Any shape you like. But no matter what you think in your head, when the sample size is large enough, okay, n is like some usually n is how large? Is it large? Usually more than 30. Okay, not very large indeed, right? I mean, if you worry, 200 will be a good benchmark, which applies to all the business application. You will have end up with the bell curve. The sample mean is a bell curve, although each individual is not a bell curve, but a sample mean will be a bell curve. So that is a very important result in statistics, right? Because we don't have to worry about what it looks like because you never know, right? How can you know how much people would like your product, right? Is it a lot of people like it? Is it not so? Is it what the shape is? I don't need to care. What I need to care is at the end of the day, the sample mean will follow the spell shape. Okay? And you ask, what's the point of in this spell shape? Because very often we actually want to know the mu, right? We want to know the mu, and that is very important. Okay. We know the mu, then we are able to, because remember what is mu, right? Mu is summary statistics. Is, of course, the best thing is to know the original P and F, right? But if you don't know, the most modest, the most first step is know the mu, right? Because mu is the most representative data, right? So we have to find out some way to estimate the mu first, right? And of course, there's some way to estimate sigma as well. And also there's some way actually to estimate P as well, but that would be way beyond our class. Okay. If you want to know how to do the P and F, there's some way to do it. But we do it in a modest way to Estimate will tell you how to guess the mu and sigma square. Okay, and as you might have already expected, how to estimate population mean, sample mean, how to estimate the sigma square, sample variance, right? Is to estimate that you divide by n minus 1. So it will tell you why in the next week. That is the right way. Why you don't divide by n, why you divide n minus 1. That is some reason behind it. Okay, but first we talk about the sample mean, which we will use to guess the mu. Is a lot of cases mu is something that we care only, right? Because it's very difficult to know what's going on. We may want to know the how it looks like, right? But we the first thing to do is look at the mu we want to guess. Is that clear what we're doing? Okay, we'll talk about that more. But this is the PV what we're doing. Okay, and that is what I said. This guy, we will say this is equal to mu, okay? And this guy will be sigma square over root n. Okay, this two is nothing new, but coming from the first one is common idea of linear property of expectation, because each one have the mean mu, so average of each observation at mean mu will be same as mu. Okay. The second one is coming from independence, right? Each observation has a mean of sigma square. Okay. And then you use the idea sum of the variance is where the sum and contrasted property variance of ax is a square variance x. We'll get that idea. Okay, I'm not going to prove it, but the proof is already in slide. But I don't want to bother with math, but this is consequence of simple random sample. Okay, and the last one is called central limit theorem. We said it will be a bell curve, the sample mean. Okay, what we're doing is the title of this slide, sampling distribution. It's talking about how the sample mean looks like. Okay, and because we want to know on average how much you want to spend your product, right? That's something is a key, right, to judge whether you want to enter the market. Right, so that is the main idea why we want to do it, because business decision involve using the past to predict the future. Of course, as a finance application, you want to care about expected return, right? And also care about the risk, right? You want to guess what is the mu and sigma square, right? How talk about the mu first, right? We talk about sigma square later, but that's you first thing to calculate is the expected return for your stock, right? You want to calculate on average what it will be the return of your investment, right? So that will be the mean. And then what we do is use the past data to calculate the sample mean, and that will give you this, and then to give you the bell curve, right? If you have a large data, that's called central limit theorem. And I also talk about another very important theorem, probably the second most important as well, is called the law of large number. We'll be giving you more detail later soon. And law of large number essentially said one thing, which you will find trivial, is if you increase your sample size, keep increasing and increasing, and eventually, okay, are large enough, the sample mean you get is exactly the population mean. Okay. Actually, it's not surprising common idea if you know central limit theorem. Look at the central limit theorem again. Central limit theorem said you have bell curve, right? The bell curve have what variance? Sigma square over n. Which means that when you increase sample size, what will happen? You will see, when you have a large sample size, we will see a smaller bell squeeze in the middle, right? Then if you increase n more, it become one line, one bar there, right? Everything is collapsed to the point mu. That's it. That's called law of large number. So when the sample size large enough, the sample mean will be as close as to the population mean as possible. It will be, you're sure to get it, basically, right? If you keep collecting data. Okay, there's no way you are not getting it. There's no other than the population mean. Okay, that's what it says. Okay. So before I break, we define the first part. Okay, and after that we talk about some special case. So far we don't restrict ourselves what kind of observation you get, right? It's talking about how much we're going to pay for a thing. It's a continuous random variable, right? Or discrete is also fine. But there's a special type of data, which is a yes/no question. For example, uh, do you like I don't know, mirror, right? Or Eden, or I don't know if Ginger, I don't know what's the name, whatever you like, right? And it's yes/no question, right? So in this particular case, uh, um, you would have everything you said apply, but you notice that uh, it will be the formula more simpler because it will related to later you see binomial trial and binomial distribution, and that will simplify our calculation. So the special case will be very useful, and because all the time you often ask yes no question, right? So are you tired? Are you happy? Right? If you look at Korean drama in old days, they will say, "Are you happy?" Right? They always the man and the woman separate, and then after that, the man asks, "Are you good?" Right? And the woman doesn't anything, just cry, and then another scene. Right? That's a similar thing. I mean, but I don't know. I don't watch Korean drama this day, but it's like 10 years ago that I watched it. It's like they said, "Are you good?" And then the woman silent for 1 minute, and that's some tear comes out, and then go to other thing. Right? That is very standard. But anyway, um, after the break, I will talk about what I said in more detail, tell you about how the sample mean looks like, okay? What's the bell curve central limit theorem, do some calculations, and we talk about the binary data case, okay? And then we'll go to a little bit more detail uh, later, okay? So for the moment, let's have a break, okay, of 15 minutes as usual. Please fill in the you reply, okay? Thank you. I see you in 15 minutes time. 冇咩唔同啊？我覺得你哋可以唔使考試。你都睇電聽啊，對於飛嚟講唔關你事。
我成日都見到，應該嗰啲係 graduate 嘅，我哋做 intern
即係 intern 唔關嗰啲 career 嘅。
好多人去聽嘅。啱入嚟嗰陣時，即係 freshman 嘅有啲人好似係唔好知嗰陣時，我哋係去聽都冇用，就照佢去聽咩 McKinsey 啊、JP Morgan 啊，全部去晒聽。
我聽下都好嘅，知道發生緊咩事，佢啲咩人，佢就講佢啲咩人，佢自己讀咗啲咩相關嘅課。
係。
不過 McKinsey 而家炒咗好多人 AI 嚟嘅，佢個 in-house AI 係難搞。
前三
AI 用得好啲咯，唔係成日做 PowerPoint 嚟搞。個時代已經過去，就對 PowerPoint 就翻。
所以我咧，我哋 PPT 咧個 deck 咧，就做 deck 嘅嘢，即係我哋個落頭寫住咩轉去上。就係啲即係 screening 就呢啲嚟，好多人嘅嚟，都係做 AI。AI 先真係啲人，之後就必去第二定考佢 AI。你有冇做過嗰個咁嘅決賽咧？成個星期係睇講嘅成佢就係同你講成日類嘅 population 咩成個 population 咁樣，一個係加，一個係減，一個要減，好似唔係正常。我差別應該係咁多人，所以要買上百塊曬地，可以用住係抽曬全部出嚟，所以有嘢再嚟。sample 係指佢喺一大個月 sample， 一大個月嗰個層次嗰個 sample，population 嚟寫嗰啲嘢就 population。sample 搞緊就係個 sample variance，佢 population 入邊抽出嚟，所以係啦，即係話你如果你有晒所有 data， 你想計佢個 variance。嗰個就係識 Muscle 係就算得㗎，但係如果你係揾 data 出嚟，佢估個識埋乜嘢咧，咁你嗰個就要計咗個減嘅。即係 sample 真係越少越大，因為你用即係你做大 MD 就知啦，係咪 ？MD 投波嗰陣時，你點樣打個關？除非你穿針嘅啫，你穿針嗰時你有反彈㗎嘛靠，咩反彈佢先會打中喎，真係。如果係 sample 出嚟減人，唔使解等嘅，你反正到時候都有識啦。係啊，我哋住喺嗰度。有機會，到時都有識㗎啦。我睇有人病，驚嘅入去。
所以我住宿舍啦，我住3年。
我哋都係做試過
我有經驗。我喺我喺屋企玩，即係80個字打上來。
住咗人。
即係有啲人跟住飛落嚟，跟住扣嘢都收幾多？
但係我租咗，我都係住喺宿舍，我係住喺我係以前會差
係啊，翻嚟㗎。
但係好到香港其實唔使住，將嗰陣時冇租。
嘅，所以買少少。但係嗰陣時我係諗緊邊個時候，跟住我以前跟住到我嘅轉同事再轉玩時再講到時，喺度簡單對佢再轉。你叫唔叫啊？新網線小號嘅糖水啊！你又佢 OK 啦，佢仲個淡啲嘅地方好犀利。我兩樣嘢都唔掂嘅。我你病嚟呢堂都可以嚟打嗰陣。
你買呢本書啊？
我後邊聽嘅。
你記得？
我邊聽啊？
交平啦。
我哋少少資料上使都叫邊家？我朋友有大家分享。我就係即係遊戲有差分，現實有差。如果你做所有方面都係差分，嗰啲嘅 research 係或者係冇如果你度 pitch 就係爭啲靚仔，第二呢要做咗佢啲 research 先啦，先做啲咩？我份學都係依家嘅，即係我 project 嚟到我嗰陣時，好似係都係點算？我都快唔齊，有朋友啦。係咩？我連參加佢都變化咯。
都係 see you live 啊！我揾到你。
你即係你咪全部有，你都放有辦都俾啊，都送啊，都係咯。我都好多粉絲，佢哋都放，我都每日同，即係
我俾答案。
我想同 discuss 答案就我你問佢攞就得答案啦。我唔可以接上去，但係擺到先，因為太衰所以信。都係可以放大我嘅。放大我嘅後果就係人大啲嘅抄，有插電啊，咁樣貼啊。雖然係又費事出咗下啲咁嘅。跟住樓上啲朋友喺度講，有啲好難。
係咪會有 class？就係 application questions 嘅。係啊。就係 last result。
基本上係用你技術人有你比較難，有參考。我單數係睇兩個邊，可以抄唔錯嘅出嚟。想玩下我都係玩啲嘅 M.Phil 嘅，加3條都少交。M.Phil 就係為我唔覺得係難啲嘅 M.Phil。係咁輸啊！不過又唔想費事拗背嘢啊。咁最簡單3條。已經好難，可能好多人就得。我呢度我靠緊嘅，攤到就慘，攤就慘。
你都算係咁啦，你錄片，我打開㗎。
俾一啲
點樣睇啊？
YouTube 有寫嘅問題完。
睇咗邊個睇？
冇，但我知道係問題。大家我知係可以全部你得8分係周學嘅，4分6版。嗰個做嚟做翻。佢哋個 offensive reply 問題 offensive slow 起好咗。他當時我對個小情況，4分3個手13幾分鐘。
所以一個 Excel 咧就係後追落嚟。
幾分10條？
我
PG 就係1題10分。10個1個分格即今日4條。攞啲字。小黃哥，好人士啊！佢真係 quiz 你 quiz 係真係想白嘅白，可能係咯，真係冇一做都講啲嘢嚟答。都成個份咁大張，7-3你做多啲得3歲，因為你10秒學到用嘅。 準備翻嚟。
我呢個可以3月中或者1月尾撥佢呢啲3個人。會啦，我咪再打2打，即係為你打3分。而家Justin 係你個 Jen 啊？
而家啲我都係即係。我都喺度食，電腦iPad 我睇落啦，
即係3個英文，
聽落後嘅，我係即係離開跟住就 OK 嘅 iPad 我上
每一天都有。
咁但係你要睇。
真係佢快要拍電啦，其實。
而家科啲人冇
有少少我實你。上堂開始好似有啲
差唔多
係上堂開始你都係遲嘅。
PF 就係咯，營養咯。因為20個。
我想租嗰啲咁嘅塞機都好似
攞寫俾自己。
哇！咁呢個真係冇所特點嘅。
你拍都要俾錢㗎嘛？
你要俾錢？
我要租㗎。
你俾錢？
係啊，我俾錢㗎。但我可以用嘅有冇所謂嘅？你還啦，佢租唔知好似100蚊100蚊都租。好揦嚟嘅，
有啲揦嚟㗎。
但係都唔係我錢嚟嘅，我都
係咁啊，咁啊，
我俾出嘅，如果係就我諗住下一年睇咪玩啲咁嘅，不過費事啦。今年我諗都唔會咁做，俾真係有人 push 嘅話，要成日睇嘅。
係啊，
我仲有一個係德國，嗰後做嘅，我係出嚟賣嘅，我唔係喺你係德國。
教。
即係冇咁樣，不過咗你又登錄嚟問我哋喺咩度，咪照答，只因你問我比較好。
係咯，佢最 highlight 咗先，乜嘢都唔知。
主要我就記得邊個，主要係記得邊個。我哋20分花住我。
係啊，呢啲咯。
So let's see what happened. Tired? Yes, everyone tired as we said at the beginning. Regardless of what you are. I'm so tired. What is the difference between big F and small f? Good question. So I hope you still remember what is big P and big F. Okay. So let's talk about discrete first. Okay. Because that is, you build intuition from the discrete. Okay. So remember what is big P. Okay. Big P is you give me a number, I would tell you the probability that the random variable equal to that number, right? For example, if I have told a coin, you have result of head and tail. My random variable is mapping number of head, right? It's a measurement. So it's a 1 and 0. So P will give you, if you give me number 0, I give you 1/2. Give number 1, I give you 1/2, right? So you give me a number, I give you probability. Okay, so that is the idea. And the big F will be the one that less than or equal to that number. So what does that mean? The big F is coming from stacking the P, you become F, right? It's like building a Lego tower, right? Look at 1 here. It's adding the red on the top, so give you the F, right? So you can always go from P to F or F to P because the difference between 2 neighboring bar will give you the value, right, of that value, right? So you can always from P to F or F to P. Okay, I hope that will be clear, right? P is just, you give me this number, I give you the probability, the random with the number. and you give me the F is, if this number, you give you everything on the left-hand side. Okay, so that's big P and big F. And what is small f and big F? The reason is when we have continuous random variable, which means that you have infinite many value you can take, then this P must be 0 always. There's no way you can define big P, because random variable in continuous means n number is possible in between. So you can, there's no single number you can pick for the P, right? Remember the analog. So now I'm still not that old, so I still have many hairs, right? Then if I pick particular hair, right, you can try it yourself. It's easier, right? I don't have much hair, but so I have some hair there, right? And if I pick it again, how likely I pick the same hair, right? Now it's still okay, right? I still cannot pick the same one, right? So means that it's unlikely to pick the same, right? Because you have a lot, right? Right? So it's not that easy, right, to have that, right? So that means that when continuous, right, then you can have the same P. But the F still apply, right? F is still fine in this particular example, right? F is still talking about the probability that less than or equal to that number is still there, the F. Okay? And the question is, do we have something similar to the P? Yes, right? The P will be the following. The small f is the area, same as what we said, stacking idea. The area, this is the F function. The area up to the point A is exactly FA, is stacking idea. Okay? And if you know calculus, if this F, the big F is smooth, you always can have some small f. Okay? That's called differentiable. Okay? And if you integrate the small f, you get a big F. You differentiate the big F, you get a small f. So if you learn M1 or M2 in your high school, you have that. But as I said, we don't require calculus, so forget about it if you don't know what's going on. So this is small and big F, okay? And you ask what this is the description of the random variable, right? For example, if your uniform, the small f will looks like this, right? The big F looks like that. Why? Because small f tells probability, right? If you say what's probability between A and A plus 1, right? It will just, you get this area with probability that the random variable is lie between A and A plus 1, right? And because of this rectangle, it's the area, and rectangle area is base times height. So that's why it's a triangle, it's a 45-degree line, right? I'm not going to tell you why, but that would be the idea. I hope I clarify that. Again, let me reiterate. If I can't answer your question, well, in the you reply, ask again. If I still can't answer it correctly, please schedule appointment with TA, right? That is very important. Use your TA resources, right? It's part of the tuition, you pay for it, okay? There's a risk. I mean, don't complain at the end, you don't know what's going on, right? Because TA is there waiting for you, okay? You should ask, okay? If TA can't solve problem, I'm the one to answer it, okay? If I can't still do it, I will be able to show you more books or AI how to help you on that one. Or if there are many questions, I will maybe have a class on that. Yes, yes, midterm is difficult. I mean, I talked to some of you in the during the break. When I was a student, I have quiz every week for this class. Okay, they have a quiz for this class. So they call continuous assessment, right? So we don't have this, luckily, right? So I have quiz for you. If you want to do it, do it. You don't do it, just remember submit. Okay. I don't count whether how many questions you do it right or have done it. So at the end of semester, make sure you submit. You get the credit. Okay. Even you don't want to do it. Okay. Just click and submit, then you get the full credit. If you don't do anything, then you get 0 for that. Okay. what do you like to do in your free time? Do I have free time? Probably not. But I mean, if do I have any free time, I mean, I take care of the kid. And no, what I do, I like cooking. I mean, to be honest, I mean, actually, most of the research I like cooking because you create something without a lot of pressure, and you cook something, cook some egg and fry some rice. Actually, now these days I cook a fairly good fried rice, and uh, I mean, I used to say if the people say a good chef able to make good fried rice, I don't get it, but now I get it. The fried is not that easy to make a good fried rice, and you have to use the good pan to cook it, the right amount of oil, right amount of thing. But anyway, what I do, and that's all I do research, right? That's what I do. Teaching will be small part of my duty. The main duty for me is that I do research and advanced knowledge. Learn how to. My research is doing game theory and also measurement. So it's just like how to do things more correctly, including the data, how to measure things, and do game theory. So how people interact. So because I'm an economist, so also I do Twitter, right? Read some Twitter. Read the news is something I do. Good morning. Yes, I'm thirsty. Retired, thirsty, coffee. My solution. Why is it still summer temperature? Well, I think it's not different from last year. Usually we will start to have the fall comes in actually in the last 2 weeks of the October. So it will be starting next week onward. You probably have a jacket in your bed. Otherwise, if you get on the subway, it can get cold because the East Rail line is super cold. So be careful. What for lunch? Um, Usually I don't eat lunch. I told you, but this is my lunch, and some biscuit in my office. We're pathetic, as my wife said, but usually these days, top people in the US to skip lunch because they don't want carbohydrate in their stomach, so they just drink some coffee and eat something. I do have a colleague from old days in Singapore. I have a colleague from I think Bangladesh. He also just only coffee for one day and then a sandwich for dinner. And they said he said the whole village is like this. Okay. I do now. I thought he was crazy, but now actually I'm that crazy as well. But it's okay. I feel very energetic without any issue. Even though if I don't eat things, say I don't have a problem. So if you're used to that, it's no problem. Of course, you should have big meal with the dinner, right? But of course, the best thing is to have big in the breakfast and in a decreasing, but I'm increasing, right? Either you have a big breakfast and middle lunch and very little dinner, right? But I have a reverse. I usually don't eat breakfast and have this thing which is my lunch, and dinner I have a lot of veggie, and that's what I do. Oh, okay, that's good. But for those of you who are writing Monday and Thursday, I guess you are deeply into the exam. Sorry, the midterm. Well, that's good. Yeah, it's too sunny, I guess. You're right. It was dry, interesting. Sample mean, yeah. Yes, large sample size squeeze the sample mean to the mean. So I think large sample size, sample mean is squeezed to the mean. Central limit theorem, that's what most important. Oh, Ginger, yes. I don't know what his name. I just know his fat Ginger. I don't know. Because it's not my generation, so I don't really get. So now we're bell shape eventually, right? It's a very nice bell shape here. The speed. And today people found it difficult to follow. More people, okay, I will try to see if I can make it good. Okay. So this one is increasing, okay? And majority of you is very tired. I can see it because that's always the case at the middle semester. So I don't understand why teacher want to give midterm because everyone is so tired. I don't know. The benefit of midterm is squeeze everything in the semester. Everyone have an exam, then You don't have time to study anyway. So that's why, to be honest, I never give, since my teaching, I never give a midterm unless I co-teach with other people, they give midterm. But in my life, I never give midterm because I really hate it. So I also never give, maybe I give some open-ended quiz in the class, but that is only multiple choice. But otherwise, I don't have, I never give midterm unless I'm forced to. So don't worry about that. You should have no midterm, and whenever I give exam, usually open book. So I mean, maybe I give one or two closed book exam, but since open books allowed it, and I always choose open book. So I hope I can still do that. But now these days you have AI. Then probably very soon we will not have exam. We will have oral exam instead of written exam. So many school I talk to these days, they basically don't have written exam anymore. So they just ask you, and then you explain. So, but anyway, hopefully it doesn't happen that soon. But so why is it if a premature baby born earlier than the full baby, the premature is considered older despite existing? Oh yeah, that's a good question. Yeah, that's a accounting problem, right? Many have to do accounting. So when you recognize the revenue, right, or recognize the cost, right, you recognize the baby is born at time. They didn't count the time. The age is not count when the sperm and the egg combine together, right? The time where you run away from your mom's stomach, right? That is how you do the accounting, right? So it's the same idea. Why you're making losses, but you didn't realize it, right? It's unrealized gain and loss, right? Depend on whether you use the accounting standard is to the gap or non-gap accounting standard, right? It depends on what you do it. So this is a standard accounting problem, right? Whether you count it, but to be sure, right, you should count the time when the sperm and the egg comes together, right? But not when the time you come out from your baby. The reason, because historically, no one knows when it happened, right? But now with these days, we know we can count it back. How old are you based on you were born? But that's a good question, and hope that accounting professor don't put in a midterm. It's not economics; it's an accounting problem. Ginger photo is funny. Yeah, I think so. I often seen his picture, right? Sometimes he can play magic, right? Sometimes very fast, sometimes very thin, sometimes very fit. So I don't know. So this is a random variable, right? Before you saw him, you don't know whether fat or thin, right? Once you saw, then you know. But before you saw, it's a random variable. It's a bell curve, right? So it's unclear. Yeah, ginger. Oh, yeah. This day, they actually, I got a lot of ginger lemon tea because very helpful for my throat because I talk too much these days. Hopefully, you don't have that. You are still too young. Mirror, yeah, that's good. Okay. So hope everyone's okay. So let me review again what we have said. Is we looking about the sample mean. Sample mean, I said again, is a random variable. Okay. Sample mean is not a number. It's a random variable. It depends on what sample you get. Okay. So that means that the sample mean will have a mean. Okay. So sample mean. The mean of the sample means population mean. So I just made a mouthful. Okay. The sample mean. Okay. Let me example here. Go back to the 1 man, 2 woman, 3 old guy, and 4 baby. Okay. Suppose I consider the sample mean. I talk to 2 person. Okay, 2 people there. I may meet Mr. 1 and Miss 2. The sample mean is 1.5. If I meet Mr. 1 and senior 3, then my sample means 1.5 is 2, right? If I have Mr. 1 and baby 4, the sample means 2.5, right? It really depends. So it can be 1.5, can be 2.5, can be 3.5, can also be 4, right? Because I meet the baby twice. Or it can be 1, right? It can be any number, right? But if you meet them many, many times, right? The average of this sample mean will be 2.5. The 2.5 is the population mean. Because suppose you know the population mean is what? It's 1 plus 2 plus 3 plus 4 divided by 4, which is 2.5, right? And turn out that if you, but you never do it, but suppose you do the sample many times. You have sample mean each time. The average of this sample mean is the population mean. But do note that you only do once. Most of the time, you don't do many. But the sample, if you do many times, then an average of those will recover the population mean. Is that clear? Okay. But do note that you only do once, okay? But hypothetically, if you repeat this many times, the average of those will get you what we want. Okay? Is that clear? Is that clear? Okay, that is what it means. Okay. We'll give you example and show you why is it true, but we'll be more we will give you a more numerical one. Okay. So the idea is like this diagram. Okay. You have sample one, we get sample mean, sample two, get sample mean, sample m, sample mean, right? But this realization depends on what they are. And turn out the average of this, okay, is exactly mu. Okay, so if you do many, m can be many, as many as you want, right? And then this mean of the sample mean, right, is the population mean. Okay, mean of the sample mean is population mean. So it's right, because sample mean depend on what you get. So many times you get many sample. One sample, you have a sample mean. The other sample is sample mean. The other sample is sample mean. And average of this sample mean with population mean. I hope that is clear. But let me give example, okay? This example. Where Mr. 1, Miss 2, and elderly 3, okay? We forget the baby 4 because why? Because baby 4 can't talk, right? So forget about baby. So, and in this case, we have 3 people there. The population mean is just adding up 3 guys divided by 3, right? Because the only 3%, right? The average. And let's consider the first case is very simple. I just talk to one guy, the sample size is 1. Okay. And if simple random sample means that each one is equally likely to be picked, right? So each one have probability 1/3. So the sample mean, we can specify the p directly because each one is being drawn equally likely. So it's 1/3. So the sample mean is 1, 2, 3 with equally likely probability, right? Because if you pick Mr. 1, the sample mean just 1, right? Just one guy, right? If you pick Miss 2, which turn out to be 1/3 probability, the sample means 2, right? Because only her, right? Adding up her divided by her, just her, right? If you get senior 3, right? Mr. Old Man 3 is 3. You get him with 1/3, right? So that's the data. So what is the expectation of this, right? Expectation is you get the value, multiply the p, and add up together, right? If you remember the expectation, right? It's just you multiply what number you get by probability, right? And add them up together, right? That is the meaning of expectation. You multiply and add, right? So you multiply 1 by 1/3, 2 by 1/3, 3 by 1/3, you get 2. Okay? What's 2? 2 is exactly the mu, right? Do remember in the real world, you only can observe one of the outcome, right? But it is saying that if you potentially do this many times, then the average of those is what you get, okay? You don't, remember you're only able to get one, okay? Because of the money issue, you don't get many of them, okay? But that is the idea. Later you will see why we do that, why we care about the mean, but very soon you will see, okay? The second one involves the same question instead of why can I move this? Okay. Instead of talking to one person, you grab two people here. Okay. So remember it's simple random sample. Okay. Which means that the first round you can get number 1, number 2, number 3 equal likely. Second round, you also get number 1, number 2, number 3 equal likely. You can get 1, 1. You can also get 3, 3. Okay. And you get 1, 1, how like 1, 1, the sample average is 1. You get 1, 2, the average is 1.5 because 1 plus 2 divided by 2, right? You get 1 and 3, you get 2, right? So these are all sample mean on 9 possible cases, right? And these 9 cases are equally likely, right? Because you can meet Mr. 1 and Mr. 1 again. And the draw is independent each time. Remember, it's simple random sample. Each one is equally likely to be drawn, and each drawn is independent. So it's 1/3 times 1/3, right? It's probability. But do note that the average, the sample average is not uniform, right? Because of you have only one case, you get 1. It's only if you have 1, right? And you have the case you get 1.5 coming from 2, 1, and 1, 2, right? 2/9, right? Which is coming from, I use other color, right? This is 2 cases. That's why 2, 9, because the 9 outcome, right? And you can have the case of 2, which is 3, 9. Why? Because it's 1, 2, and 3, right? You can have 3, 1, 2, 2, or 1, 3, right? That will give you 3, 9, and so on and so forth, right? Add up is 9 possible cases. Okay. And then you have this 5 situation, and you multiply them by probability, right? That gives you the expectation or the mean of sample mean, right? The 9 cases, right? But actually, you can summarize into 5 outcome, right? So just multiply. Okay, it's 2. Of course, you can do it in easier ways. Multiply this by 1/9 and then add up to everyone. It's all the same. Okay, because just the same as L. Okay, just 2. So 2 is what? Same as the population mean. Okay, so I demonstrate to you that the mean of the sample mean is population mean. Okay, and now is the time to trust me, brother. Is here. You have 3 person you talk to. Okay, you have this big P function. You can try it by yourself. Okay, there will be totally 27 possible outcome. Okay, you can just actually draw it out. Okay, but I'm not going to do it. You can draw a tree there. Okay, trust me, this is the answer. You will get 2 again. Okay, that you can imagine if you have 4 or 5 or 6 or 7, actually it's still 2. Okay, no matter what you do, the average of sample mean is population mean, no matter how big the sample size is. Okay, and the proof is already in this slide after, but I'm not going to do any proof. Okay, so just trust me. If you don't trust me, trust the slide. Okay, that will be there. There's a proof behind, but I'm not going to show it to you because we're not math class. So the proof is just one slide. There's a proof. It involves the only idea of linear property of expectation. Is the first line is because multiplied by constant, you can take it out. This step, and this is expectation of sum is sum of expectation. And once you're done, use the independence. This is done. So I'm not going to talk about the proof, but in case you care about the proof, this is how I prove it. But as I said, this is not math class. But in case you want to study more math, that's how you can do it. Okay. And if I didn't explain correctly or you don't get it, you don't really see what's going on, you can feed the slide to AI. They can explain to you line by line. That is easy, right? Because slide don't have emotion. You can keep say you don't know, then he will try to explain. Okay. But again, our TA also very nice. Okay, you can ask her. Okay. And the second thing is what about the variance of sample mean? Okay. Why you care about that? Remember, you care about 2 things, right? The basic thing is where the sample mean is centrally located, and how variance of this is how good is the sample mean, right? And turn out that the sample mean, okay, is closely related to the variance of the population, okay, and but it's divided by n. Okay, what does that mean? It means that if your data is really spread out, your sample mean is also very spread out. Makes sense, right? Because your data is very spread out. You get the sample from there, right? The sample mean can also vary, right? Because your data is very spread out, right? You can imagine the data is like instead of 1, 2, 3, 4, right? It's 10, 20, 30, 40, right? The sample mean will be much, variance is much larger, more spread out, right? Instead of they concentrate to each other, right? Or you can imagine this easier thing is, imagine a society is very equal. You got the average income, doesn't really matter you get, right? Have very little variation. But you go to society, a lot of rich people and a lot of poor people, you try to get the income data, The average, depending on who you talk to, has a large variation. Right? Very easy. Or maybe you go to my house, my home, I look at my wardrobe, you will see I only have this blue t-shirt, white t-shirt, black t-shirt, very boring, right? But if you try to look at my daughter's wardrobe, then he has many different kind of colors, different kind of style, right? Or that would be much more variance. Why? Because my variation of my clothing is very small variance, right? For her, it's much bigger. So you try to grab something from her wardrobe, then will be much larger variation than mine. Okay. So, and here y is inversely in n, right? The answer is also very simple. If you only get one object out of what you have, same as original one, right? But you get more and more, you get more and more stuff, the variation is very little, right? Because you basically look at everything there, right? So once you look at everything there, then the variance drop. Okay. Of course, this is a math result. You can prove it. Is coming from, as I said, the property of the variance. Okay. And the proof is somewhere at the background. I'm not going to do it. It's just it's just also one slide, the proof, but rather I will show you the result. Okay. Sorry, show you the example. But before we show you the example of variance, let me talk about a special term which you often see. It's called standard error. Okay. Standard error is the term that it's a standard deviation of a statistics. Okay. Standard error of the mean means standard deviation of sample mean. Okay. Okay. It just you error, you can. So what does it mean? Error, when it's error, it means deviation of the sample. So this is very mouthful. If you say error, is the standard deviation of the sample, and that is the equivalent thing. Why they do it, I don't know. I would prefer to call it a standard deviation of the sample X. Okay, sample mean, sample variance, sample whatever. But that is what people call. So that's okay. I don't want to disrupt that. And remember, we have sigma square over n, right? And basically what you do is to take square root of the both sides, right? Square is gone, square root, so this one. It's the same thing. Okay. So that is and turn out that this is very useful. Okay. Very soon you will see. Okay, it's very useful. You will see. We'll use a lot of time in the class. Okay, so that standard error. Standard error nothing but standard deviation of sample. So error means the same terminology. Okay, that's why right here, right? Standard deviation statistic cause an error. Now let's convince you that the standard deviation of the statistics or sample mean, right, will be the population variance over n. So look at the question again, number 1, number 2, number 3, right? Mr. 1, Miss 2, and old man 3. Okay. Again, the population mean is 2, which we know it very well. Okay. And the variance is just subtract each observation by the mean and take square and do everything, right? Get 2 first. So now look at the sample mean of size 1. Okay. We know that on average you get is 2, right? Because this is the mu, right? And let's look at the variance. Okay. If you get 1, has 1/3 probability. This guy is 1, right? 1 minus 2, -1. Square is still 1, right? If you get 2, 2 minus 2, 0, square, 0. 3 minus 2 is 1, square is 1. Okay. So this guy, square difference from the mean is 1, 0, 1. So expectation of this is the variance. You just multiply and add, right? So that's why it's 1, 1/3, 0, 1/3, 1, 1/3 is 2/3. 2/3 is what? Same as this guy. Why? Because it's sigma square over n, and n is 1 here. Okay, n is 1, you get 1 sample. So is when you have 1 sample, the variance is same as the population. Okay. Now you consider case we have 2. Okay. Sample size 2. Okay. And we have, remember, have 9 different cases, but collapse to 5 outcome, if you still remember. And you can do the calculation, say 1 minus 2 square, 1.5 minus 2 square. This is what the outcome is. There's typo here. This should be 9. Sorry. This should be 9 here. Okay. And you can calculate the variance, which at 5 outcome, right? Multiply by the second row to the last row of the table, and add together. And you can figure out that the answer is 2/3 over 2, which is what is sigma square over n, where n is 2. Okay, so I demonstrate this formula is correct. Okay, of course, the proof, just 1 page of math, is this at the a few slides after. I'm not going to work on the proof, but that is always true. Okay, that means that regardless of what you're looking at, right? So this is always true. Okay, is true for n equal to 1, 2, 3, 4, 5. So it doesn't really matter, regardless of the n. Okay, is that okay? Now, once we have that, I mean, this is go to 3. I'm not going to talk about that. Okay, once of that, we have we call law of large numbers, as we said already. Okay, remember the mean is just the mean of sample mean is just population mean, right? The variance of sample mean is just population mean divided by n, square sigma square over n. What does that mean? If n go to infinity, what happened to the variance? 0, right? So the sample mean is population mean. We have very large sample, right? Very large means that, remember, we only have 4 guys or 3 guys in our data, right? Mr. 1, Miss 2, old man 3, and baby 4. What do you mean by n go to infinity? Means that we actually only have 4 guys, but we do it for 1 million times, right? Or 1 trillion times, right? But at the end of the day, we do so many times that eventually this variance becomes it's nothing. Okay, and you look at the data of infinite long observations, it's exactly mu. Okay, of course, no one can do infinity, but it means that when you have a very large sample, then this eventually get what we want. Okay, and that is the idea of science in some sense, right? Because we have so many observations about the laws of physics. So that's why we say physics something is something observed. We believe the Newton law is going to hold, right? We believe the Einstein law is going to hold, right? Less so in business world, but because we don't have enough observation about business, right? But the physical world, we know very well. I mean, many things we observe, it's going to be true, okay? Because of this idea, right? Because we know we have so many observations from the history, from the old days, from historical time to now. We know that, right? If you jump out of the window, of course you'll fall down, right? You're not going to rise up, right? So we know very well the gravity, right? The apple falls on your head, right? That's Newton observed, right? So if you study, you pass exam. You don't study, you fail, right? Even though we don't know enough time, but you know enough history that it's not going to have variation, right? There's no way that, I mean, you don't study, you get 100 points from our exam, right? So that's something that we know very well. So formally, what's law of large number? It just say the probability, the random variable, is within a small distance from mu will be 1. What does that mean? You mean the following. It means that, remember, mu is a fixed number. What vary is this guy. Okay? So what it means is, this is mu, which I don't know. Okay? But I can have mu minus epsilon, small number, as small as you want. Okay? And it said, this X bar, okay, 99.9999% will be within this range. Okay, If you do 1 billion of time, maybe 1 or 2 here, but almost everything is here. You can have this as small as possible. Okay. And of course, how big is this number depend on your sample size n. Okay. If you get a bigger sample size, this range will shrink smaller, right? When n goes to infinity, this basically go to almost to 0. Okay. But I don't want to talk about the epsilon delta definition, which you learn in the M1, which is M2, or you learned it in the math class. So it's epsilon delta definition. Okay, but anyway, I don't want to go to the detail, but this is the formal definition of the law of large number, which I have to put it. Otherwise, you don't know what I'm saying, right? Because it's just like the probability that it can be outside epsilon is 0. It's basically 1. Okay, basically it's 1. So only thing you can find is within a small range there, right? Because you cannot say it's continuous, right? So you cannot say probability. You can only probability or range. Okay, you tell me where's small range of that. Okay, that will be within this small range. Okay, I hope that's give you a precise idea what do you mean by law of large number. Okay, although I put the you put it in the purple box. Okay, there's no way in this class I ask you this. Okay, the reason I put it because I don't want it to be black, because although it should be black, but this is so important. If I put it black, doesn't do it justice of this theorem, because I said this is a one of the most important thing you learn from this class, right? You mentioned in other class as well. So this is something I want you to know. Okay, this definition, this proof here, but I don't want to go to that. And as I said, this is a law of large central limit theorem. After that is a central limit theorem, right? Which essentially said when n is large enough, this become a bell curve, right? As I said already, right? So there will be mu is here, right? Is look like bell, right? Because we know it will be somewhere around here by law of large number when n is large. But how it approach there, it is going to be a bell shape approaching. Okay, it will be a bell, and the bell is squeezing the middle. Okay, so that is the idea. Okay, remember it regardless of how the original population looks like. Okay, which is, as I said at the beginning, in this one. Okay, doesn't really matter the original one, the orange one looks like. Okay, it can be bell or no bell, but at the end it's bell. Okay, regardless of so that's a very powerful theorem, right? Because without this, we don't need to study statistics. Okay, this is the bell curve that allow us to study statistics. Without that, things will be very terrible. Okay, we don't have to take this class. So you all enjoy accounting class, right? We can't predict the future, right? So we just based on accounting look at the past, right? So because we have probability class with statistics, because we can look at the future. How to look at the future? Central limit theorem. Without that, nothing works out. Okay, so basically you will see why we can work for the rest of the semester. It's based on a bell curve. Without a bell curve, we're done. So you may not be surprised to see the bell curve, right? This is what we have in old days. So you can see if 1, 2, 3 is equally likely. Okay, if you draw one sample, what you get is the 1, 2, 3 here, right? So you have sample of 1 look like this, right? And you have 2 look like this kind of style. Okay, it's 1 eye, 2 third, 1 third, right? And you have 3 look like this. Okay, and you have 4, you look like this as well. Okay? And you can imagine if I have larger sample size, it would be very similar to what I observe, what you see here. Okay, so that ends the bell curve. Okay, so this is the formal definition of central limit theorem. Not fully formal, but more or less right. So it says when n is large enough, the sample mean is approximate normal with mean mu with variance sigma square over n. Okay, and remember standardization. Okay, you just minus the mean and subtract the SD, right? The standard error, right? Standard deviation of that, which is take square root, this is a sigma over root n, is a normal CO1. Okay. So the first part is centrometer theorem, and this is just standardization, right? There's nothing new here. This is from the last chapter, but this is what we call centrometer theorem. And probably you ask, how large is large for this rule to apply? And it's not that large. You only have 35 is done. Okay. And that means that when you do business, we're really less than 35, right? So centrometer theorem always apply to your application. Okay. So you may ask actually when you see less than 35 in the real world. Yes, you do. Go to medical school. How many examples they have? Maybe 20 or 10 even, because they do operations, so they can't do a lot of data. So very expensive to get one data set even, data point. So let me have this example before we go very quickly. So we have the population with sample mean 5, where we're in 64. So mu is 5. Sigma square is 64. Okay. And sample size 100, n is 100. Okay. And what's probably the sample means no more than 4. So that's the question. Okay. And you know by centrometer theorem, because n is more than that, this is what you get. Right? So once you know this is normal, you just apply the same idea, you get to it, right? Because if you calculate this is the variance is 64, right? That means that is 8 over 10, this 0.8, right? So this is point. So the sigma x bar is 0.8, right? Because you take a square root of this guy. Okay. So we're asking is this 4 is here. Sorry. Mean is 5. Okay. We are taking 4 here, right? But 4 here is what? It's actually 1.25 SD, right? Because SD is 0.8, right? Which is square root of this guy. So basically, is Z here, right? We ask this area, right? This is 0. This is negative 1.25. We're asking this area. Because less than 4, right? Is asking is 1.25 SD below the mean, which is asking this Z is less than 1.25. And this from Excel is just norm as this negative 1.25 true. So this Excel will give you negative, sorry, 0.1.5. Okay. You can also set the Z table as well. Okay. So don't worry, you will learn this Excel when you do the assignment, right? So I know you're very tired. Don't worry, we'll repeat this example again next class, so you don't miss it too much. Okay. So enjoy the rest of the day. I will see you on Friday. Hopefully you get good luck for your midterm. If I'm a little bit rushed for this example, I'm sorry, but we'll talk about that again next class. Okay. See you. Good luck. Everyone's very tired. I know, because I'm tired as well.
係啊，日本頭髮住啊，講驚咯，嗰陣時咧，
都唔係大，因為時間好少。
佢落人去加油，佢嗰啲咩誒快有。